Have you ever wondered how the microchips in your devices are designed? Microchips, those tiny pieces of technology, are the lifeblood of our digital age. They're found in everything from your smartphone to your microwave, even in your car. They're the reason we can communicate across the globe, navigate our way to new places, and even cook a meal in minutes. Microchips are the silent heroes of our daily lives, working tirelessly in the background, carrying out billions of operations each second. They are the epitome of human ingenuity, a testament to our ability to shape the world around us. However, these little marvels are not as simple as they seem. Behind their minuscule size lies a complex and intricate design process. Each microchip is a labyrinth of circuits and transistors, all precisely designed and arranged to perform specific tasks. The complexity of their design is akin to a symphony orchestra, where every instrument plays its part in harmony to create beautiful music. This intricate design is made possible by a process called very large-scale integration, or VLSI. VLSI is a method that allows us to integrate hundreds of thousands of transistors onto a single microchip. It's a flowchart of design steps, each one just as important as the last. The VLSI flowchart design process is like a roadmap, guiding us through the creation of these technological wonders. It begins with specifications, where we define what we want the microchip to do. This is followed by RTL coding, where we translate these specifications into a language that the microchip can understand. Then comes simulation, where we test the design to ensure it works as expected. Synthesis, placement, and routing is where the physical design of the microchip comes into play. Finally, we have fabrication, where the design is brought to life. The creation of a microchip is a journey of precision, creativity, and technical prowess. It's a testament to our ability to manipulate the smallest of components to create something that has such a profound impact on our lives. So are you ready to delve into the intricate world of VLSI flowchart design? Let's get started. Let's delve into the intricate world of VLSI flowchart design. The magic behind the microchips begins with the VLSI design flow. This process is like a wizard's spellbook, containing all the steps necessary to transform a simple idea into a complex, functioning, integrated circuit. It's a journey that begins with a concept and ends with a tangible physical object. VLSI, or very large-scale integration, is the process of creating an integrated circuit by combining thousands of transistors into a single chip. It's like putting together an intricate puzzle, where each piece has its own unique role and place. The first step in the VLSI design flow is the specification stage. This is where the concept for the chip comes to life. Think of it as drawing a blueprint for your dream house. You'll need to define what you want your chip to do, how fast you need it to work, and what technologies you'll use to build it. Next, we move on to RTL, or Register Transfer Level Coding. This is the stage where the chip's behavior is defined in detail. It's like writing the script for a play, where each actor knows exactly what to do and when. After RTL coding comes the simulation. This is where we check if the chip behaves as expected. Think of it as a dress rehearsal before a play's opening night. It's a crucial step to ensure that everything works perfectly. Once we're happy with the simulation results, we move on to synthesis, placement, and routing. This part of the process is like building the set for our play. We decide where to place each actor, how they move around the stage, and how they interact with each other. Finally, the last step is fabrication, where the chip is physically made. It's like the final performance of a play where everything comes together. In essence, the VLSI design flow is a complex and intricate process that requires careful planning, precise execution, and meticulous checking. But at the end of the day, it's all worth it when you hold that shiny new chip in your hand. Now that we have an overview, let's explore each step in detail. Every great design starts with an idea, and microchips are no different. Now let's delve into the first tangible step, the specifications. Think of specifications as a blueprint, outlining the desired functions and performance of the chip. They set the stage for what the chip is set out to accomplish. Specifications encompass various aspects such as the operational speed, power consumption, physical size, and the overall functionality of the chip. These elements are meticulously planned and documented to serve as a guiding light throughout the design process. For instance, if we're designing a chip for a smartphone, the specifications might include low power consumption for longer battery life, high-speed processing for seamless multitasking, and a compact size to fit within the sleek design. Specifications are the foundation of the chip design, setting the parameters and goals for the rest of the design stages. With the specifications in place, it's time to bring our chip to life. Ever wondered how a microchip knows what to do? That's where RTL coding comes in. Let's dive into the fascinating world of register transfer level, commonly known as RTL coding. This is a crucial step in the design flow of very large-scale integration, or VLSI. RTL coding essentially bridges the gap between the human understanding of functionality, detailed in the specification phase, and the hardware language that the microchip understands. In essence, RTL coding is all about describing how data flows through a system and how that data is processed. It's akin to creating a roadmap for the chip, detailing where to go and what to do along the way. This roadmap is written in a hardware description language, HDL for short. There are several HDLs out there, but two of the most popular are Verilog and VHDL. Now, you might be wondering, what does an RTL code look like? Well, it's a series of interconnected registers with data flowing from one to another. Think of these registers as tiny storage units, each holding a piece of the puzzle that makes up the overall functionality of the chip. Between these registers are combinational logic blocks, which perform operations on the data as it moves along. RTL coding is a meticulous process. It's like crafting a complex piece of machinery where each gear, each cog, must be precisely positioned for the whole system to function as desired. And it's not just about functionality. Designers must also consider power consumption, performance, and area, the three key metrics in chip design. Remember, chips are at the heart of our digital world. Every time you send a text, take a photo, or play a video game, you're relying on these tiny miracles of engineering. And RTL coding is the blueprint that guides their creation. So, the next time you marvel at the latest tech gadget, spare a thought for the RTL code that makes it all possible. After the RTL coding, it's time to test our design. Before constructing a building, we test the blueprint. Similarly, simulation is our blueprint test for microchips. Imagine you're an artist, and you've just finished drawing your masterpiece. But before showing it to the world, you want to check if all the colors are in harmony, if the figures are in proportion, if the overall image resonates with your original idea. This is what simulation does in the world of very large-scale integration, or VLSI. In the context of VLSI, simulation is the process of verifying the functionality and performance of the register transfer level, or RTL design. Think of it as a virtual trial run for our microchip design. It's where we get to see if the chip is going to perform as expected before we move on to the more expensive and time-consuming processes of synthesis, placement, routing, and fabrication. What makes simulation so crucial is its role in identifying and correcting errors in the design. Just like our artist wouldn't want to unveil a flawed masterpiece, we don't want to proceed with a flawed chip design. After all, the stakes are high, and so are the costs. A single error can lead to a non-functional chip, wasting not just our resources but also our valuable time and effort. During the simulation process, the design is subjected to a wide range of scenarios and input combinations. This is done to ensure that it behaves as expected under different conditions. If any discrepancies or bugs are found, they are rectified at this stage itself. One might think of simulation as a form of quality assurance. It's our safety net, ensuring that our design is robust, reliable, and ready for the next stages. In essence, it's our final checkpoint before we proceed further down the VLSI design flow. So the simulation stage is where we put our design to the test, identifying and rectifying any errors, making sure that our microchip is all set to perform just as we envisioned. It's our way of ensuring that our design is not just good, but great. Once the simulation is successful, we move on to the next stage. Now that we have a viable design, it's time to create our microchip. Our first step is synthesis. In this process, the RTL, or Register Transfer Level code, is transformed into a netlist. Now you may wonder, what's a netlist? Well, think of it as a blueprint of our chip, detailing all the components and their connections. It's a crucial intermediary between our high-level design and the low-level physical layout of the chip. In the synthesis process, each high-level description of a digital circuit in the RTL code is converted into a set of generic logic gates. This conversion is done through a library of predefined logic gate templates, The result, the netlist, represents the same functionality as our RTL code, but in a format that can be physically implemented on the chip. With our netlist in hand, we move on to the next step, placement. Here, the components of the netlist are arranged onto the chip. This arrangement needs to be optimized for performance, power, and area. In other words, we want our chip to function efficiently, consume minimal power, and occupy as little space as possible. Algorithms are used to find the best placement that balances these factors. After placement comes routing. This is where the magic really happens. The components placed on the chip are connected using wires, forming the intricate network that makes the chip function. The routing process also has to balance performance, power, and area. Too many wires can cause the chip to overheat, while too few can limit its functionality. At this point, our chip is designed and laid out. The synthesis, placement, and routing processes have given us a chip that meets our specifications and is ready for physical realization. We've transformed our high-level design into a tangible physical object. With our chip designed and laid out, we're ready for the final step. Finally, it's time to bring our microchip to life. This is where our journey through the labyrinth of very large-scale integration, or VLSI, takes us to the final station, fabrication. Fabrication, in the simplest terms, is the process where the design of our microchip is physically etched onto a silicon wafer. This is where our intricate design becomes a tangible reality, a microchip that can power the devices we use every day. Imagine the silicon wafer as a clean canvas, ready to be transformed into a masterpiece of modern technology. The process of fabrication is akin to a highly precise form of artistry, where the artist uses advanced tools and techniques to etch patterns on the silicon wafer. This process begins with the application of a light-sensitive material known as photoresist to the silicon wafer. The wafer is then exposed to ultraviolet light through a mask that carries the design of the chip. The exposed areas of the photoresist become soluble and can be washed away, leaving behind the pattern of the microchip etched on the wafer. This is known as photolithography. Following photolithography, the wafer undergoes a series of chemical treatments to remove or add materials in various areas as per the design. This process, known as etching and deposition, forms the various layers and structures of the microchip. Then comes the process of doping, where impurities are introduced into the silicon wafer to modify its properties. This is crucial for creating the active components of the chip, such as transistors. Finally, the wafer is cut into individual chips, each ready to power a device. Remember, this is a highly simplified explanation. The actual process of fabrication involves many more steps and a great deal of precision, carried out in a cleanroom environment to avoid any contamination. And there you have it, the complex but fascinating journey from an idea to a working microchip. This is the magic of VLSI design, where creativity meets technology to transform the world around us. We've journeyed through the fascinating world of VLSI design flow. We've navigated the intricate pathways of microchip creation, from the conceptual to the concrete. Let's revisit these steps like beads on a string, each vital to the whole. We started with the specification, the blueprint of the design. This forms the nucleus of our project, the heart from which all other steps flow. It's a roadmap detailing the performance, power, area, and functionality of the design. Next, we delved into register transfer level, or RTL coding. This is where we translate the specification into a hardware representation. It's akin to an architect transforming a client's vision into a detailed plan. It's a critical step, bridging the gap between concept and reality. Simulation followed, a vital checkpoint in our journey. We tested our design against a variety of scenarios, ensuring it can withstand the rigors of real-world use. It's equivalent to a building undergoing stress tests to verify its sturdiness. Then we explored synthesis, placement, and routing. Synthesis is where we convert our RTL code into a gate-level representation. It's as if we're building the walls of our structure, brick by brick. Placement and routing follow, arranging these bricks optimally to ensure efficient use of space and resources. Finally, we arrived at the fabrication stage. This is where our design takes physical form, where it's imprinted onto silicon wafers to create an integrated circuit. It's the culmination of our journey, akin to the completion of a building. Each step in the VLSI design flow is complex and significant, demanding precision and expertise. They're interconnected, each one building upon the previous, shaping a pathway from concept to reality. It's a testament to the marvels of modern technology, a symphony of engineering and design that brings our digital world to life. Next time you use a device, remember the intricate design process that makes it all possible.